I tried recording to get a higher quality by recording to the iPad, and I just got a message that says memory is full. So apparently that doesn't work. So I'll have to record to the cloud now. So there it is. CPU, well, let's say, this is the chip. Here's the chip. And all the stuff I'm describing resides on an Atmel 328P Arduino chip, which can come either in the format of a leaderless chip carrier or a surface mount device, or even a dual inline package. And we've seen that in the Elgo systems that we've been able to find inside the lab. So that's kind of interesting. So let's drill down a little bit more into what's going on into this control unit. We have a bus from our CPU, and inside of this bus, we have something called interrupt control. And this is all on chip, interrupt control. And as I had said in the past, you cannot find multitasking inside of your Arduino. But what you can find is interrupt-driven processing, which is kind of like multitasking, but a little bit different. And what you can do with interrupt control is you can have external interrupts come in. And you can have timers, which are inside of the CPU, which will give you internal interrupts. And you can program the timers with great precision. Also, on the CPU, you have a thing called, and this is I/O, I guess we put it in the I/O area, the serial ports. And these are the things that will allow us to do I/O through the USB interface so we can print to our console. And so now you've got just a little bit more detail into the microcontroller. I'm not going to draw out the registers because I don't think that adds anything to the discussion. But what you have is RAM, ROM, your CPU, your timer, your serial port, and your I/O all on a chip. That's very characteristic of a microcontroller. Microcontrollers attempt to integrate as much of an entire system as they can. 2 kinds of memory, interrupt capability, timers, serial ports, ALUs, and for I/O, I guess you could also include things like your analog to digital converters, which have external inputs going in. And you might have 6 or 10 different I/O lines coming in. So that's kind of nice. I mean, people like that sort of things for a microcontroller because it's supposed to control something. It's supposed to. And that is about all I wanted to do to discuss the overall architecture. What I really wanted to do during this lecture is to zoom in and do a deep dive into this part right over here called interrupt control. And that is kind of a different kind of programming that you're not used to. What's going to happen is something either in a timer or external to the CPU is going to generate an interrupt. And it's not a round-robin scheduler like we're used to with a task manager. It's different. Interrupts come in. They may have priorities, but once they come in, the CPU stops what it's doing, pushes its state onto the stack, and then jumps to service the interrupt routine, runs the routine, then returns from the interrupt, pops off the stack all of its present states, and then continues its execution. In the event that it gets lost servicing the interrupt and doesn't get back to the present execution thread, something unexpected will happen. It'll look like your CPU is crashed. It'll look like it's non-responsive. It will never get to return from the interrupt, and you'll wonder what happened. Or it won't return, it won't service the interrupt fast enough. This is one of those things this is where art and science kind of come together, because servicing the interrupt quickly enough is really important. And sometimes, and this is very unfortunate, you could interrupt the interrupt. And if the interrupt gets interrupted, then you get deeper into the weeds as you go to service that interrupt. And you can imagine how complicated the code will get then. So if interrupts are being interrupted, then you've got another thing interrupting the interrupt, and the question is whether or not the interrupt will want to permit it. So now you can do things like masking interrupts, which means stop all the interrupts from happening during the service of an interrupt, which means you might actually lose one of the interrupts that come in. What would be an example of an interrupt? Why would we want to interrupt the CPU with anything? Yes, sir.
Well, to give you an example with the panning code that I did the ultrasonic on, I had to interrupt the panning every time I made a step so that I could read the ultrasonic sensor.
Well, you could have done that sequentially. You could have taken a step, read the sensor. After you read the sensor, then continue.
That's true.
No, here's why you want to interrupt. Let's assume I have a telephone and it sits on my desk. I wonder if somebody's calling me. Well, I'll just pick it up and listen. Hi, anybody there? Oh, no. Okay, put it down. I wonder if anybody's calling me. Oh, pick it up again. Oh, hi, anybody there? Nope, nope, put it down. Right? That's called polling. That's very inefficient. Nobody wants to sit there. I wonder if somebody's calling me. Here, just a minute. Oh, nope. Okay, never mind. Put it away. So that's no good. So what happens is we develop an interrupt, which allows us to shift our context. I'm focused. Neil is down, working on my next, what do we call this? Homework 4. Oh boy, homework 4. That looks like a good one. And then the phone rings. What do? I put down the homework. I answer the phone. And it's telemarketers going beep, 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 beep. You need a warranty for your car. And we're going to bother you until you cry for help. And I'm like, I hate this. Oh my God. And what was I doing? That's a high overhead context switch, right? Because why? Because I was interrupted. Somebody interrupted me. Or I'm busy, heads down at work, and the boss says, here, this is your top priority item. Get this done now. And I say, oh, holy crap. Okay. I put everything else to the side, and I start to work on this, work. It's 2 in the afternoon. I skipped lunch. I got it all done. I said, here, boss, it's done. He says, great. Get back to work. I said, oh, okay. So I go back to work, and I go, what was I doing? I got interrupted, right? I had another high overhead context switch. So at some level, interrupts happen to us all the time. Same thing happens in the CPU. You can interrupt the CPU for any one of a number of reasons. You can have something external to the CPU that's completely asynchronous. Back in the day, I had my uncle's reel-to-reel tape recorder, and it was electronically controlled or electrically controlled with a microphone. It could do fast forward, it could do rewind, it could do record, it could do play, all from the little handheld microphone. It was so cool. It ran with tubes. And what I did was I put a little magnet on the side, and then I put in a reed switch, which is a magnetically operated switch. And every time the magnet was in proximity, it would close. That generated an interrupt for my little microcontroller, so it could know how many spins. It was my odometer, how many spins went around on the reel. And then you could queue up and find programs that were stored on audio and coded onto the tape and download the audio programs. It was kind of like a poor man's magnetic tape drive. Normally,
anytime you're doing anything asynchronous, you need that, right?
You need it. You need it. If you want the microcontroller to wake up when somebody walks into the room because you're building a burglar alarm, then maybe what it does is it says, hey, the PIR sensor just went off, and checks to see if the windows are closed and checks to see if it needs to make a phone call to the police because his alarm was set. Right? So at some level, there are lots of different asynchronous things that can happen. you could have, the ring system essentially do a motion alert on your little phone that says, hey, there's somebody at your door, because somebody rings the bell. You start taking pictures, and you wonder what it could be and who they are and whether or not you need to let them in, because it's maybe a contractor who has to gain access to your house to fix your whatever. So interrupts are part of life. We get interrupted all the time. And it certainly can be a part of a signal to a processor. And usually the interrupts can be driven by external events, but they can also be interrupted by internal events. So for example, let's assume, and this is a real example, I have a DAC, my digital to analog converter, my SPI interface, SPI, here's my DAC, external, but with an SPI interface to the I/O. And what I want to do is I want to take a signal in from my ADD converter, do some processing, but I want regular sampling. So every 25 microseconds, I want to come back, get another sample from the ADD converter and push it into my stack for processing. And I want to output something to the DAC. I want signals to continuously flow because it's a stream. And I want to make sure, because I need uniform sampling, that I have a timer that goes off every 25 microseconds, and that's going to give me a nice, fast sampling rate. I can make it as fast or as slow as I like, assuming the hardware can keep up. Maybe 25 microseconds is 50 kilohertz or something like this. So it's a pretty fast sampling rate. And if I decided to do stereo, maybe I would sample each thing and pump it out to 2 DACs, and then I'd go a little slower for each DAC because I may not have enough CPU oomph to do the processing. So that's done with a timer and interrupt control. Another great application, and one which we will see. So the interrupt is essentially allowing us to run a background task which wakes up and executes at a precise time. You can't do that with microsecond precision inside of most of your desktop computers, because they're not real-time operating systems. But this is all running in real time. Not to say that you couldn't get a real-time operating system to run on your laptop or something like this. I don't know anybody that actually does that. Even the Raspberry Pi computers usually don't see them running real-time operating systems, usually. So where would we see this architecture? And the answer is we see it at the heart of the ATmega 168 and the 328. So the 168, that's the earlier version of the Arduino called the 2009, which is Italian for 2009. And then the Arduino Uno, which uses the 328P. And finally, I think there's a whole pile of new ones, Megas and 2540s and whatever you like. Maybe just more interrupts and more of everything. So that's a built-in instruction set architected system called jump to service subroutine, and there's an interrupt service routine, and there's a return from interrupt. And these are all mnemonics for machine codes which are implemented in the instruction set architecture built in to the CPU. And you will find that in a wide variety of CPUs in one format or another. One format or another. So the interrupt service routine, which is over in here, that's something you have to write and associate with in your main code. So far what we've seen and I'm going to erase this now, but I'm going to relate this to the architecture of your program. So far I've seen the setup that executes once, returns void. And then there's some kind of a loop, void. It's called the main loop. And this gets invoked for us continuously. And somewhere down at the bottom, I would like to have sort of my subroutine for doing interrupts. Returns void. And what I need to do in my setup is associate this interrupt service with something that's going to trigger the interrupt. So I have to have an external trigger. Let's take a step back and take a look at how that might work. So suppose I have a timer. We'll call it timer 2. And it does an interrupt at 62,500 kilohertz. Say 62,000.5 kHz. This is exactly the kind of timer I need to generate interrupts for me in order to be able to keep up with a digital signal processor that's going to do audio. What I'll do is I'll take this thing and I will divide it by 2. This is my attempt at writing a flow chart. And if it's an integral number of 2, then it's going to come out to be like 31,025 kilohertz. 31.25 kHz. And I can divide that by 2, and I can rely upon precision from these things. Right? In other words, I'm hoping that I'm going to get correct numbers when I start dividing by 2. Half the time, I'm going to read from my analog to digital converter. And the other half of the time, I'm going to read from another ADC. And this will give me uniform sampling. And once I read from this one, I'm going to say I have a sample flag equal to 1. And when I read from this one, I'm going to have a sample flag equal to 0.
What's a sample flag?
It's just some flag I set up so I know whether I've read from here or read from there. When it takes a while to do a read on an AD converter, these things don't return answers immediately. They have to start their own little timer, and then they have to do successive approximation until they reach the voltage, and then they signal that they're done. So reading from an AD converter takes time. You can have the AD converters run a little bit faster if you only have one of them running. But the dirty little secret is the Arduino only has one AD converter. And all they did was they took an analog multiplexer and allowed a register to direct the input to the different AD converters. So it says it has 6 AD converter inputs. Internally, there's just 1. And so you have to share the resources of the successive approximation timer counter and the associated internal DAC in order to be able to do an AD conversion using the internal AD converter. If you have an external AD converter, all the bets are off and everything I said is wrong. But using what's in the 328P, you basically have to choose which AD converter you're using. You can't have them converting at the same time. And then you go and you want to start the next conversion. While you're busy, and this is the exit for the interrupt. So all of this happens in an interrupt service routine that essentially allows you to do uniform sampling. This is an interrupt service routine, and it executes at 62.5 kilohertz. And that's pretty cool, actually.
So what would this be useful for?
Sampling from the AD converter to give you an analog signal from two channels, channel 0 and channel 1, at a specific rate, and pump those things into the signal processing loop, which is going to be over in here, perhaps checking for this flag. And when the flag goes to 1, it says, aha, I have another thingy and I can do the processing. And what you're looking for is uniform sampling. So this will keep the sampling uniform, provided that the interrupt doesn't take too long. And it kind of doesn't. This is pretty fast. Meanwhile, the loop has got to do some kind of processing and pump out output to the DAC. So this makes for a synchronized sampling system, right? Synchronized in time because you've got a separate timer. And it allows you to do a kind of software interrupt, right? This is software. Although one could make a compelling argument that the hardware of the timer is hardware, it's built into the CPU. So because we're able to do a kind of, I'll call it hardware interrupt in software, we can make things that are synchronous. This is controlled. Now I could associate an external interrupt and it could be asynchronous and that could come in. So you can have external interrupts come in hardware that are asynchronous. I guess the senior project team is leaving. They have something else to do. If you want to mask the interrupt, you can. And maskable interrupt requests are possible. And what you do is you use an interrupt mask register. This is the IMR. And what that'll do is when you're in the middle of an interrupt, you might want to mask any other interrupts that come into your system because you might not want your interrupt interrupted because that would make things work badly. And then there are non-maskable interrupts. Non-maskable interrupts, or NMRs, non-maskable interrupts, might be things like watchdog timers. And these will be high priority tasks that you don't want interrupted. You can establish them as non-maskable. So this is a presumably a maskable interrupt, but you can set it so it doesn't get interrupted. But if something bad happens, like you start running out of batteries and your watchdog timer wakes you up and says, hey, look, your batteries are running down, this can be interrupted even if you set the mask, because the non-maskable interrupt of the watchdog timer has priority. So it's a very, I call it rudimentary priority system in the interrupt system of the Arduino. Let's see now, what else we got? If you want an external circuit, physically, pin 2 and pin 3 are your external interrupts for your Arduino. And you can wire directly to those and then associate them with interrupts. And unfortunately, they map to interrupt INT0 and INT1. You'd think they would map to interrupt 3 and 4, but they do not. So pins 2 and 3 are mapping to interrupt 0 and 1. And so if you wanted to do the wiring with a push button and generate push button interrupts by pressing on a button, well, you could, but you have to go to pin 2 or pin 3 and map that to interrupt 0 or 1. Those are your external interrupts. Other Arduino variants have more interrupts. The timer. This timer is asynchronous with respect to the CPU. It's a separate timer, an asynchronous timer. It's external to the CPU. And therefore, it runs asynchronously with respect to the main program. That's that gives us a little bit of opportunity now. We have some time, so I'm going to draw a picture to talk about exactly how to wire this stuff up. Because there are precision timers available only on certain pins. So we have pins 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 on the I/O system. 11, this is timer 2. 10, this is timer 1. You get the output directly from there. And timer 1 has 2 sections associated with it because it's a high precision timer. So this is the A section and that's the B section. Because it's a 16-bit timer, whereas this is only an 8-bit timer. Five is timer 1 input. And 6 is going to be an output for the A section of timer 0. And this goes on and on. So you can kind of see how the timers can be accessed. You can set the timers, and you have 16-bit timers and you have 8-bit timers. And these are constraints of the hardware chip. This is what's inside the chip. You can't control that, but you can control which timer you use. So when you were using, when you were doing pulse width modulation with the servos, we were hooking up to something like, I think it was pin 9 or something like this with the servos. We were using some part of the timers. And you can use it whether or not you're using the servos, but the servo library was using that timer system for pulse width modulation. Changing the duty cycle of a square wave with the timer is a cinch when you're doing a subroutine library like the servo library. The timer 1, which is over in here, that's a 16-bit timer. And if you're using the servo library, then that resource is consumed. You don't get it. You don't know how to use it if you're going to use the servo library at the same time, because that'll create a conflict. And resource contention is a big deal at a microcontroller. You have to know what resources are being used. When you call the servo library and you start using timer 1, you don't get to use it for other things. You've got to allocate to somewhere else. So you were using it without even realizing you were using the timers. So now let's take a look and see what we can do to associate ourselves with a timer. We'll do it in setup, and what we'll do is we'll create an interrupt with timer 1. And this is going to be, I think, your first actual programming example. Now we've got a good background. So here comes your setup. And what we'll do is we'll set pin mode. What this does is it establishes a value in the data direction register. So we'll go to pin 13, we'll set it up as our output. That's normally where we'll plug in something like an LED. So we put the LED in pin 13, and the other side of the LED goes into the ground. And then what we're going to do is we'll go to timer 1, and we're going to do initialize. And we'll put in a number. Let me count the zeros. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's in microseconds. A million microseconds is a second. This is a high precision timer, right? Timer 1, 16-bit timer. And now what we'll do is we'll go to timer 1, and we will attach an interrupt. And we'll attach, I don't know, something like timer LED. So we'll put the LED on a timer so it blinks in the background. Every time the timer expires, the LED blinks. And because we're working in microseconds, we can expect this LED to continue to blink in the background while we do whatever we want to do in the foreground. So the timer LED code is going to do a digital write and we'll put in pin 13, and then what we'll do is we'll do a digital read. And we'll read from pin 13, and whatever is being read, we'll do a exclusive OR. So if it's a 1, exclusive ORing 1 with 1 is going to give us 0. If it's a 0, exclusive ORing 0 with 1 will give us a 1. So that'll invert whatever it is we read, and we'll write it out to the LED, causing the blink. Now our loop doesn't have to have anything. It can have whatever we want. It can have anything or nothing. Because we are now blinking the LED in this timer LED thing, which runs in the background in accordance with the built-in hardware 16-bit timer inside the CPU. What do you think of that? So that's our first subroutine service routine. And that is almost what we have time for. So it's going to blink on and off every second. You can do whatever you want to in this loop, and it will continue to blink in the background, just as though you had multitasking. But it's not multitasking, it's interrupt-driven programming. And this is your very first example of interrupt-driven programming. What do you think of that? So timer LED is a name of some sort of function which exists already in this code that's being passed in by address, being attached to the timer so that when the timer expires, it will invoke the subroutine, stopping this loop just for long enough to be able to write out a value, read a value, and then it'll return to the loop. You can put whatever you want to in that loop, and you never have to worry about having the LED blinking in the background, because it'll always be blinking. What do you think of that? Any questions about timers? How about you guys in Zoom land? Any questions about timers? No? So what we can do is we'll have a little lab about the PIR sensor that should be available to you. I also made a little video for you so you can see that. And then you guys can use the lab to come in and set it up just like we did before. Were there any questions about the lab we did last time about servos in the last couple minutes? No? No questions? All right, so we're doing it this way with very simple labs for everybody to do very quickly and then leave, because we only have 1 hour in which to do the labs. And I think it's better that you have a hands-on organic experience. And if you want to, just set it up and leave, you can, but sometimes it's fun if you can set it up and get it working and then play around with it a little bit and use the full hour. I've seen some people leaving right away, and I know you can do that, and that's all right. But you might as well get as much out of it as you can. And I'm going to keep the labs relatively short, just so that we can split the time between the two sections. So that's what I got for you for today. Stay safe. Thanks a bunch.